Bismillah ar-Rahman ar-Rahim. Welcome back to lecture number 4. We have just finished in the previous session talking about the color spaces, color models, the RGB, the CMYK, and we have seen some examples on this issue. Let's continue and share with you the screen of our slides. Here, as you see, in the previous session, we discussed the color perception and spectrum, color and its attributes, color spaces, and let's go further and continue our lecture 4 by talking about the image classifications and image types with some demos and examples. In general, we can broadly classify images into three major or main classes. The first class is what we call it the raster-based. The second type is the vector-based, and the third one is the meta files. Let's have a look on every one of these classes. If we start with the raster-based images, here as you see in the slide, raster-based images or raster images are files that store actually every pixel in the image in a sequential format. As you know, when we deal with files, we store and record or maybe save these files in the form of binary 0-1. So we are sequentially, in this case, storing pixels in the image into this file. As here, when we zoom this part of this image is as raster based, and this is the result of zooming. And as you see here, we have the pixels consisting the details in this image. This process will be continued until we finish or we scan all the image and convert it from two-dimensional into binary sequential, let's say vector or row of digital bytes or bits. In case of the vector-based, as here we can see that in case of the vector-based, we are, instead of storing the pixels themselves, we're going to store a list of operations or actions or equations that describe the location and the properties of the objects making up the image. So for shapes, for arcs, for lines, this is a very useful tool to store these images. As you remember in the AutoCAD lab, you could sketch and let's say you have dealt with let's say different 3D components or piece of material, and you constructed it on AutoCAD. Now, in this case, we are going to store, instead of storing the pixels themselves, we are storing descriptions and list of operations that can be done on this image. Examples on files that use this sort of vector-based images: PDF, EPS, AI, SVG, CSV, etc. All these images are, all these files are storing images in the form of lists describing the details instead of storing the pixels themselves. As you see here, if you look at this part, this piece here, you can see that this small circle, when we zoom it out, we get a clear image. While in the previous slide, as you have seen, when we zoom this part, we get pixelized output. This is normal because we are storing pixels, and when we zoom, we just duplicate these pixels to get a larger size. I have also here, for example, if you look at this image, here I have a circle, a red circle with a boundary which is dark. This image is circle raster. I call it circle raster.gif. Here, as you see, that you can see simply that the edge or the binary or the boundary of the circle is very clear that we have some block effect. It looks like small blocks containing or constructing the image itself. While when we look at it on the original version, where we have it on Word, it's just a circle. I have tried to zoom into the same size about 500 times, 500%. You see that when we zoom it, we see that clear cut edges, and there is no pixels seen, because in the Word, when we insert a draw, or we insert a circle or shape, we are constructing, or we are giving instructions to, and when we save this image, we are saving inside the word, of course, we are saving it as a list of properties and a list of instructions to draw the circle again when we open the file from its beginning. So as you see that, it's very simple to understand and see that the raster-based images are useful for real scene or real world scenes, or real images, while for, let's say, some applications we may use vector-based, and they will be very useful and very clear and cut for the viewer for zooming and for processing and handling. Now, can we see the third type? The third type is the meta file type, or the meta image type. In this case, we have images inside. As here, in this case, we have a part is, let's say, vector, and the other part is what is, let's say, raster. For example, this is a medical image for some medical applications. I think it's maybe CT or MRI. I'm not expert in this field. However, you can see that we have details about the images captured for this patient. And we have some details here. If you look at this part, you can see some details about the patient, about the instruments used, and about the exposure type, time, file of the patient, etc. All these things can be found in meta files like the DICOM format, which is very well-known, DICOM format, which is very well-known in medical applications. Let's have a deeper insight about it. So this is again a medical image with some details inside the file format. This is the image. It's a raster-based part, okay? A raster-based part, while here we have some info about the image. If we zoom it now, so you can see these details. For example, we have here the exposure type, the filter type. We may see also other things like protocol name, contrast, etc. All these things are related to the device or the system that captured this image, and it is saved and recorded inside the file, which we call it by meta file. So the meta file contains a part which is raster, which is the usual image. Could be grayscale, could be RGB, it could be anything else. However, and it contains also other details about the image, details and list of properties and information about this image content. So now we get to the final stage of describing this course or this lecture. The first demo is about binary images. Binary images. What is the binary image? Binary means either 0 or 1. So, for example, we call it sometimes monochrome. Mono, one, chrome, color. So one color. In this case, we have the pixels are stored in a sort of a single bit, either 0 or 1. Either 0 or 1. So the 0 will be maybe black and 1 may be white. So this one, a very simple image here, as here we have either black or white. So here we have black, here also we have white. Okay. Now, actually, if we want to talk about the image and give it more specification, I think that you need to know and to be familiar with the used here coding. In this place, we have it's true that it's 1, but 1 means white, and white means 255. While for the black, this means that 0, but we mean by 0 again black, which is 0, 0, 0, 8 times. So we have 8 bits for 0, for example, and here we have 8 bits for white. So when when you store an image binary, when you let's say reconstruct it, or when you display it on a screen, the screen or the code or the program will convert the 0 into 8 0 bits, and the 1, which is 255, the maximum color, gray color, which is the white, it will be 8 ones and we get 1 byte of 8 bits having all values of 1. Okay. Maybe I missed the ID here. We have here 64 by 480 image for this case. So we have here, let's say, 640 by 640 by 480 maybe pixels. Okay. This will give us 640 by 480 by 1 bit. This is how what we store, and this will give you finally something like around some value which is in bit. If you want to convert this into bytes, you just need to divide this by 8 to get how many bytes you can obtain in this image. This is the simplest form of images and usually used for scan imaging or maybe on some documents to get either black or white. Now for the grayscale images, here every pixel is stored using a value between 0 and 255. Again, 0 is black and 255 is white. If you have negative modulation technique, sometimes you can use it. Also, you can get there 8 bits. You can get there the white in terms of to be 0 and the black to be 255. No matter, you don't care with this. You have finally 8 bits per pixel. So in this case, we are going to deal with 8 bits per pixel. So in case of having 640 by 480 grayscale image, this means that you need to multiply this number by 8 bits to get maybe around 2.4 kilobytes. When you multiply this by 8, then you divide by 1024 because 1 kilobyte equals 1024 bytes. Roughly speaking, 1 kilo means 1000. Now, if you use 8 bits, sometimes in medical applications, we may get, instead of having 8 bits, you may take 12 bits. Recently, we could also use in some applications, especially when we deal with medical images for better resolution, we may use 16 bits per color or per for the grayscale. And this will give us a higher and a larger size because we there need more details and more resolution to get better judgment and decision on some issues. In this case, when you take 12 bits, you need you mean that you have 4069 gray colors. So if we look at the 8 bits image, let's set up another color. 8 bits per pixel. This annotation. This means that we represent every pixel by 8 bits. Now we may use 12 bits per pixel. So we get in this case 12 bits. Okay. In the first case, we have 2 to the power 8. This will give us 255. While for the second case, we will have 2 to the power 12, and this will give us 12. This will give us 4096 different gray levels. So as you look, as you see here, if you look at these numbers, you can see the difference between the resolution. Here we have better resolution in case of 12 bits. For sure, when you want to get more resolution, if you want better, you have to pay more. So this sort of resolution, of course, as we mentioned in the previously, it's what we mean by is it spatial resolution or spectral? For sure, here we are dealing with spectral resolution because the number of quantization levels are higher and higher. Okay, so in this case, let's have a look on these images. These images are all grayscale images or with 8 bits per pixel. These are familiar images. This is for layman, this is for sailor, and it's from the internet. I selected this picture. I love this this look in the eyes of this kid. Now, when we deal with true color or RGB color images, in this case, we are going to use 8 bits per color component. So, suppose that we have RGB, so we give the R 8 bits, same thing for G and for B. This will give us 24 bits per pixel. This can be converted into the different color that can be produced using 24 bits, 2 to the power 24. This will give us 16 millions or more color variations. So that we call this as a true color image because it covers all possible colors that can be captured or sensed by the human vision system. And this means that we multiply, instead of having one 8 bits per pixel, we have 3 8 bits per pixel. So we need 3 bytes to represent these images. So this means that we need more and more size and more bits to represent color images. This is an example on this image where this kid, this sailor kid, I think that it's also enjoyable to have a look on this view or on this image. Sometimes we may need to display a color image using only 8 bits maybe. How comes to display a colored image using only, let's say, 8 bits or maybe 6 bits? This leads to invent the indexed images. What we mean by the indexed images? Let's have a look on this idea. Now, we use some sort of compression techniques, lossless compression. We are not going, lossy compression. I'm going to use some details in the color image to reduce the size and keep a good and pleasant output. Instead of having 24 bits, we may just classify or have maybe 8 bits or 256 colors in the image. So the main idea behind the indexed images is the following. Having an image with true color, 24 bits, I can represent this image by taking only the most frequently used colors that has these colors that have the highest probability of occurrence. So the pixels are repeated in this image. We try to get the highest repetition in the image and select the highest 256 color repetitions. In this case, we construct a matrix to indicate that these colors are represented in a table. In this table, we just order it from 1 to 256 and give every row in this matrix a color triplet RGB. Maybe not clear now. Let's have a look on this example. Okay. Here, as here we have an RGB image. We go to the image pixels now here in this case. This is a point, a specific point, image or point in the image here, as you see here. This is a pixel. And we want now to represent it using the indexed image type. So we sort the pixels in the image in ascending order from the highest repetition down to the lowest. And in between, what we do, let's have a pen with a smaller size. Okay. Sorry. Okay, let's have this one. Now, after ordering the matrix in this form, so as here we have RGB components. And we give the index of 0 for the first one that has the highest maybe of the 256 indices and sort it in this way down to the number 255, where we have the repetition, the most 256 repetitions in this image. So instead of transmitting the whole image or saving or keeping all image components, we give a code of index. So this pixel is repeated very frequently, the highest repetition, and we'll give it a code of 0 using 8 bits. Why 8 bits? Because we selected 255. Well, of course, we started from 0, so we have 8 bits to represent this code. Then 1, this will be again using 8 bits, but with another code, up to the 255 to get 8 ones to get 8 bits to represent this pixel. Then we stop. Now, in the original image, we just simply, as simple as this, we just need to replace the pixels in the image that with the highest repetition appearing in the indexed file. In this case, we get the image stored as 8-bit image. Of course, do not forget that you need to store also the matrix or the table that was used in producing this index. Okay, I'll try to explain this in a simpler way. Let's have a simple example this way. Just a minute. Now, okay, let's have another pen, for example, this one. Now, you get some image. This image is RGB. Of course, the RGB contains 3 layers, one for R, one for G, one for B. Let's say this is R, this is G, and this is the last one is B. Yeah, it's a sort of 3-dimensional matrix for this B. Now we are going to produce the table. In this table, we have the following. Here we have the index. Okay. Here we have the R, G, and B components. R, G, and B components. We scan the image here and see the repetition for each triplet having how many times has been repeated. And we, for example, let's say we'll take in this time index 0, 1, 2, maybe, and let's use 2 bits, 0, 1, 2, 3. Okay, so we just produce this matrix, and here we register or we keep the values for the RGB. Okay, now instead of sending, for example, this pixel, we go to the table and look for which one is close to this pixel value. And let's say that it was somewhere related to pick or something like this one. So instead of sending the RGB value, which is 24 bits at this location, we are going just to send the index taken from this index from the first column. And in this case, it will be 2. We just need to represent 2 in binary form to get it will be 0. Let's say, for example, 0, 0, 0, 0, 1, 1, 0. So we use 2 bits. Okay. Now, how to understand this? On the other side, we need to have the same matrix or table. We call it the palette. We need to have this palette on the other side. So there's a program that will be saving and extracting or displaying the image from the palette that is already given on the other side or on the decoder side. We read the code. Okay, we go to the matrix to row 2 and extract the values of the RGB components from there. This will give us, of course, a very compressed image, because instead of having 24 bits, we are just transmitting 2 bits, and this, of course, there will be some errors. Usually we use 8 bits, maybe 12 bits, instead of 24 bits. So the compression or the compactness will be maybe 50%, more or less, depends on your choice and on your taste. You need to compress more, or you need to have some pleasant output or some pleasant view. So in this case, we can use the indexed images, index type of images, to indicate or to give some indices to a specific color triplets. How to select these color triplets? We can select it from the image itself from here, and in this case it is selected based on the repetition or the minimum. Why we need the repetition? Because you'll find out that in this unstructured data that this repetition will be very important in producing the output image after being compressed using the index format. Okay, let's enter all these things here. One of the good applications for the indexed images is the GIF file format, GIF, the GIF file format, where you can see images. Of course, here let's have examples on these things. Let's change this one. Okay. Sometimes you can get some GIF animated images or GIF animations or Java animation, where you have very simple and very compressed files with many slides that are repeated in a specific manner and a specific speed to give you some, like this one, happy birthday image that looks like a video. It's not a video, it's just a sort of animation that can be very helpful and to be transferred over the internet and to be saved on your computers or your mobiles. When you look also on the images, now we get here, if we zoom this image a little bit, this one, again, zoom it again. Here we have on the left-hand side, okay, let's move this one somewhere in here. When you look at this image, we have 8-bit color depth, and here we have 24-bit color depth. What does that mean? Here we have a color image RGB with 8 bits per color, which means there are 24 bits. Now we constructed the matrix in the index form and get this image. For you and for me, I think, you cannot see very big difference between the two images. And for someone, maybe you may see that it looks similar. In fact, it's not true. When you look some places like here, the background, you can see the difference here. If you look at the background, you can see that some distortion when coming from the 24 to the 8-bit depth images. However, still acceptable and of good quality and can be saved on computers very easily and very simply. Okay, let's have an example. Here we have given an RGB image of the size 800 by 600 pixels. Of course, here we have the image RGB. This means that 24 bits. And if you will compress or if you will store this by your image by 24 bits, this will give you a very large size. It will be 800 by 600 by 24 bits or 3 bytes. Now, what is required here is calculate the file size without header. Why without it? What is the header? The header is the where we have some information about the file. This will be discussed in the next lecture. And in the header, you can put the palette or the table that we have just mentioned before. Now, if the image is to be converted to grayscale format, then calculate the file without size without the header. Of course, again, without the header. Any file format, any file is like BMP, PNG, all these formats have headers. But in case of this header is very small, few bits or maybe a few hundreds of bits. Now, if the image is to be converted to an indexed image, and in this case, we want to use a color palette of 512 triplets. 512. This means that the matrix size is 512. This is converted into 9 bits because 2 to the power 9 gives us 512. Then calculate the file size without the header again. I'll keep part 1 and 2 for you and to solve it. Now let's go to the question number 3. Here the image size is 800 by 600. Now the color palette size will be, of course, we have 800 by 600. This is by 24. This will be applied to the compression indexed image compression technique, and we replace the 24 bits required for each pixel by 9 bits, because we have 512 tricolor triplets. Now, number of bits per image will be 800 by 600 by 9 instead of 24. Of course, divided by 1024, because we need to convert from bit to kilobit. We have got something like 4 megabyte, 4.2 megabit, 4.2, around 4.2 megabit. Now the number of bits in the palette. What is the palette? It's the table. So the table is ordered from 00 up to 512, 511 in this case. So we have, in this table, we have RGB pixels sorted from the lowest, or from the highest to the lowest, having 512 rows, starting by 0 and finishing by 511. So we have 512 rows multiplied by why 24? Why 24? Because in the palette, as you remember, in the palette, let's see this one, we are going to save 3 color triplets, 3 color components. And here we write 0, this is the index, 0, 1, 2, 3, up to 511. So in this case, we have this row, this one, etc. In this row, we have how many bits? We have 24 bits. Also here, we have 24, and so forth down to the, so what is the size of this table? It will be 512 by, how many bits are used here? 24 bits. And this will give us the size of the palette. This is the palette. Now, when we add this to the size of the image, what is the size of the image? In the image, we have every pixel in the indexed image is represented using one of these color triplets encoded using 9 bits. Okay, and this will give us the total size of the image. So the number of bits in the palette is 500 by 12 by 24, and this will be about 12 kilobits. Now, what is the final bit rate? What is the final total size? Now, we have the number of bits per pixel, per image, 800 by 600 by 9. Why by 9? Because we replaced 24 bits by 9 bits from the table. This will give us, as you see here, the number for around 4 megabits, plus the size of the palette, which is 512 rows having true color, 24 bits, and this will give us 12 bits. So the total size will be something like just around 4.2 megabits. Okay. Now compare this with the original size. When we take the color as true color, 800 by 600 by 24. Instead of having 9 bits, we need to multiply by 24 to get the original true color image. A reduction of about maybe up to 60% will be achieved using the indexed image. Of course, there will be some distortion. However, we can accept to get a reduction of maybe 2 or 3 times with losing some few details in the image. It's up to you if you want to use it or to keep your original size with the pleasant view as you wish. So that's all, talks, and I hope that we'll see you on the next lecture, inshallah. Assalamu alaikum.